Okay, so yesterday we left off at number 27, where the question was asking us to take a look at the potential and the kinetic energy for both the shoes and the boots, and to figure out whether if we throw both the boots and the shoes, if they were thrown at the same time, which one will hit the ground first. Anybody has an answer for me? Anyone?
Is it 27?
I'm sorry?
Are you talking about
Number 27. If we threw them at the same time, if we're assuming that both of them were thrown at the same time, which one will hit the ground first? Just a quick reminder, okay? Just so you remember, we talked about the fact that the first one, or the shoes, the height for the shoes was how much? 20 meters. The height for the boots was how much? 35. Okay? So this is closer to the ground. The shoes is closer to the ground. The second thing that we would look at is the speed. So the speed of the shoes was how much? 20 meters per second. Yet the speed of the boots was 7 meters per second. So which one was faster? The shoe. Which one is closer to the ground? The shoe. So which one will get there first? The shoe will. Now if it was the other way around and the speed was much slower, then I would expect the boots to get there, just because boots are heavier and, you know, based on the speed. If I want to make sure, I can go ahead, I can always assume that my time is constant and use distance to find speed times time will give me what. So quickly, just so we can do this, the distance of the shoes would equal to your speed times time. And I'm assuming that we are thrown at the same time, so I can plug in same time for both. And then distance of the boots is equal to, gentlemen, the speed of the boots times the time. So for this one, speed is 20 times, I'm going to assume the time is 1 minute. And for this one, speed is 7, I'm going to assume it's 1 minute. Okay, 7 times 1 is 7, 20 times 1 is 20. It takes 1 minute for the shoes to go 20 meters, and it takes 7 minutes, it takes 1 minute, because we assumed it's the same time, to cover, for the boots to cover 7 meters. So this also tells me that the shoes are faster. We're good? So we can make sure, if you are not sure about your answer before you answer, you can always use the distance and plug in a time that is constant for both. Same time for both. Okay, so that's for number 27. Number 28 said, if 200 joules of work are done on a coffee cup raised off the counter 2.5 meters, how much force was applied? Okay. So I have work to be 200 joules. I also have, what is 2.5 meters? Distance of 2.5 meters. Which formula best fits? We know that the formula for work is equal to what? Force times the distance. In this case, we are being asked for the force. So I can go ahead and find force by doing what? Dividing work over distance. What is my work? 200. What is my distance? 2.5. 200 divided by 2.5 is equal to Isn't it 80? It's 80. And what is the unit for work? Joules. And that will be my answer. That's the answer for number 28. 28. Yeah, that's the answer for number 28. Yeah, that's what I said. Number 29. 29, all you have to do is plug in the information. This is the law of conservation of energy. What does the law of conservation of energy say?
Energy is transformed, never created or destroyed.
Awesome. So energy is neither created nor destroyed. It is just transferred from one form into the other. Awesome. Okay, so the next problem talks about energy transformation. And unfortunately, when the printout made it, the image was not properly transformed onto the paper. So I'm going to go ahead and draw it for you again. So this is what the image should have looked like. Okay, and then we have A over here. Okay, this is the beginning of the ball rolling. Then B is around here somewhere. Then I have C. Then I have G. Okay? So the scenario says a ball starts at rest and at point A and rolls down the hill and then back up. You first have to rank the positions in the order from greatest to least amount of kinetic energy. Then you have to rank the positions in order from greatest to least amount of potential energy. Now, here's what I'm going to do. This is greatest to least. Now, if you guys remember, when I talked about this, we went over the questions for the roller coasters. We talked about the energy transformation step by step, okay? And then we showed it in the form of a color on a circle. What happens as the ball or as the roller coaster goes down the coaster, okay? So I'm going to quickly remind you of that by drawing a circle, and you could tell me what's happening to the energy at these points. So if I have the circle up here at point A, what am I expecting to see in terms of kinetic and potential? What do we see? Complete potential. So this will be complete potential at A. Okay? Now, as soon as, and I'm going to pick a new point, I'm going to say down here at point X. Okay? What happens down here? What happens at point X? Complete kinetic energy. Okay? So if I look at my circle, I know I'm going to see all complete kinetic. So the energy, the potential energy transforms into kinetic energy, into energy of work by the time it reaches here. So what happens somewhere in between? I'm going to go back to B, and I'm going to say, okay, so at point B, my energy transformation looks like so. Who can tell me what it looks like? So there's a little bit of transformation of energy. So you don't see half, you don't see all the way. You see just a little bit of kinetic, and the rest of it is still potential, because At this point, you have some transformation, but not complete transformation. Okay? So around this much. Okay? Now, as soon as we move away from the complete kinetic, which is over here, the red point, okay? What happens on this side at point C? What can you tell me at point C? What's happening? Do we remain at complete work energy, complete kinetic?
No.
What's happening?
More kinetic than potential.
A lot more kinetic than potential, but you start to see potential being reserved again because it has to do what? It has to recharge as it goes up the hill. So, and it slows it down as well. So I would say that over here, it is mainly red, but some of it starts to charge as black, or we can say potential. Okay? So let's look at D. What happens at point D? Is it all potential? Is it all the way back up?
No.
So what's happening? At this point, I can say, because it was not going as fast as this side, and it does not regain all its potential back. It is around 50-50. Therefore, if you look, it should be kind of like so. Half potential, half kinetic. Okay? So now I believe that this made your life easier when it comes to answering the question. Kinetic energy, greatest to least. How can you rank these? Wyatt. Greatest kinetic is where? X would be if I had X on the question. Since I didn't have X on the question, I'm still gonna put it because I drew it down. So X would be first. C is next. D. B. A. Okay? Now, what about potential energy greatest to least? Louder. B. D. Louder. C. And then X, of course, if I asked you for X. Now, what did you notice? It's backwards. Exactly. It's just backwards. So, when I have the greatest potential energy, that is the least amount of kinetic. When I have the greatest amount of kinetic, that is the least potential. And as the transformation happens, you see it happening slowly, but one way or another. More potential, less kinetic, more kinetic, less potential. Because that's how work happens. Any questions? Okay, so this was the end of your review.